first talk is on optomagnetic sensor using NV sensors in diamond for biomedical applications by Kelly, Daniel, Jake, and Ben.
Thank you. My name is Daniel Pepler, and with me today is Jake Rochman. We'll be presenting our project on an optomagnetic sensor for using NV sensors in diamond for biomedical applications. To give a brief overview of our presentation, first I'll begin by talking about the application, background, and motivation of our project. Then Jake will talk about the device physics and implementation, as well as our design choices. I'll then talk about our experimental methods, and Jake will conclude by talking about our experimental results and conclusions. So for the motivation and background and application, we'll be concerning ourselves with surgeries involving the physical removal of tumor cells. So currently, MRI imaging is the most common technique for creating a biological image. MRI works by creating a spatial map of molecules in nuclear magnetic resonance under an applied electromagnetic field. It has both high sensitivity and is non-invasive. As you can see in the top left image, the person just sits in the machine while it takes the image. And the image below it shows a typical MRI image where the black region in the top left corner of the image is where the cancer is. MRI imaging provides a location and can in some cases determine whether a tumor is benign or malignant, and in some cases can also determine the stage of the cancer. A new technology in MRI imaging is the use of superparamagnetic iron oxide particles. Typically, gadolinium is used as the contrast medium in MRI, but for kidney-sensitive patients, it can be toxic. So SPIOs, or superparamagnetic iron oxide particles, are used instead. These SPIOs are important to us as they pertain to the implementation of our device. So although MRI is a great diagnostic tool, it has limited use during surgery due to the bulkiness of the equipment, and the detectors can't be placed inside of the body because they require cryogenic temperatures to work. So this means that surgeons will rely on other techniques during surgery to have feedback during surgery. So currently, during surgery, surgeons will remove the tumor cell, and then they'll take biopsies of the surrounding tissue and then stain them and examine them under a microscope to determine whether or not there's still cancer. And then after which, if there is still cancer, they'll either have to continue surgery, or if the patient's out of the surgery room, they'll have to go back for additional surgery. So this process is it's not ideal because it takes a long time, and either this patient has to be under for a longer period of time, or they have to be returning for additional surgery. So there's a need for a device which can be used during surgery to monitor and track the surgery's progression. So our device that we propose needs to be able to measure the molecules in the human body. It needs to be small to not increase the invasiveness of surgery. It needs to be able to probe within the body, so it needs to be biocompatible, and needs to give the surgeon real-time feedback. So our design concept is a lensed optical fiber with a microdiamond at the end containing characteristic NV defects. These NV defects can be probed with green laser light, and then they'll red photoluminescence back, which gives us our magnetic properties. So a device such as this can be implemented if before the surgery, the patient was treated with these SPIOs, which would then be tagged to our target species, in this case, tumor cells. After the surgeon's removing the tumor cells and they think everything's gone, they would then use our probe to determine if the magnetic field of these magnetic particles is still present, after which they would either choose to continue with surgery or know that they have completed surgery.
Okay, so I'm going to talk about some of the properties of the sensing medium in our device. So very quickly, the optical properties of diamond. It's a very attractive material due to its wide band gap, which allows it to be optically transparent through the visible. It has a large thermal conductivity, which is useful for any high-power optics. And you can make isotopically pure diamond, which can be useful for like quantum optical applications. So more specifically, we're interested in the nitrogen-vacancy defect in the diamond structure, which can be seen here by replacing a carbon atom with a nitrogen atom and an adjacent carbon atom with a vacancy. So this molecular structure creates a bright luminescent point defect. It has optical and microwave accessible electronic transitions. We can optically initialize the spin state, and from this we can get spin-dependent luminescent properties, which I'll go over now. So here's the energy diagram of our NV center. We have a ground state and excited state, each with a spin triplet. We can excite an electron from the ground state to the excited state using green light or a 532 laser, and we'll get a red light to come down. And these are spin-preserving transitions, typically. We can also have this non-radiative process where an electron in the plus or minus 1 state will non-radiatively decay to the 0 state, and this is where we get some unique properties. So we can also look at the Zeeman effect, where we see the splitting in the plus 1 and minus 1 levels, and this is linearly dependent on the external magnetic field. So now we want to go through how can we use this to do magnetometry. So as we see, as we increase the strength of the magnetic field, the spacing between these energy levels will increase. If we sweep a microwave frequency about these resonant frequencies, we'll see a dip in photoluminescence. And this corresponds to the microwave being on resonant with the 0 to plus or minus 1 transition, which will allow this non-radiative process to occur. So in summary, NV centers are bright luminescent defects in diamond. They have optical and microwave accessible transitions, and we can use this to exploit or to determine the local magnetic field. So in terms of different diamond materials, we can use bulk diamond, diamond microparticles, diamond nanoparticles, or some engineered structure, where here is something like a waveguide, which can control the propagation of the optical mode of light. So if we're going to quickly compare some figures of merit to determine which is most useful for us, so we can see that our microdiamond satisfies most of these criterion, mostly due to its large enough that it can have lots of NV centers, so we can get a lot of signal, and it's also small enough that we can integrate it with our device. Also, we can look at the optical fiber component. So typically, optical fiber can be classified as a single mode fiber, where the core, which guides the light, is on the order of 4 microns, or a multi-mode fiber, where it's on the order of 50 or 60 microns. We can also, instead of just having a cleaved fiber with just a facet, which will allow the light to disperse, we can add a lens on top of or on the fiber tip, which can help guide the light and collect it more efficiently. And we're also going to compare this to a microscope objective just for clarity. So if we look at, again, some figures of merit, we can see that the lens fiber is our optimal solution due to the increased coupling efficiency compared to a normal fiber, and we can easily integrate it with our device. So just to bring them together, we have microdiamonds, where they have a concentration of nitrogen of around 150 parts per million. They're then irradiated and annealed to create the NV center defect. And these have a coherence time of about 1 microsecond, which is a useful parameter to determine the sensitivity. And they're also on the order of about 15 microns in diameter. Also, our lens fiber can be characterized by these few parameters. It has a 10 micron working distance, a 2 micron spot size, and a small numerical aperture of about 0.1. So we can simulate trying to couple these together. The image on the left, we see the spatial distribution of the coupling from a point source and coupling into the fiber, which is shown by that rectangle at the bottom. We can see as the gap distance between the two increases, that the efficiency decreases. For the simulation, we didn't account for the lens nature of the fiber, just for simplicity, but we can see that we can get an efficiency of around 1% using this system. So how our device can meet the requirements, it has a small size We have large sensitivity due to our characteristic NV centers in our diamond. We can get fast readout because our NV centers are bright and we have a lot of them, and we can integrate it with other components, which allows it to be useful during surgery.
Now I'll go over our experimental method. So first, we designed a module which allowed us to align our optical fiber to our diamonds. Then we coupled this module to the existing free space optics setup. We then used our module to align our fiber to our diamond, and then we performed our optical magnetometry experiments. So in this image here, shows a simplified version of the optical setup. So the laser produces our green light, which then is reflected off the diachroic mirror. The beam is then focused into our fiber coupler, travels through our lens fiber, excites our NV, which then red photoluminescence, and then that is collected back through the optical fiber, and then the red light passes through the diachroic mirror, and then a long pass filter is used to attenuate any leftover green signal, and then our photoluminescence counts are measured through our detector. Here's a setup of our alignment module. So the lens optical fiber was attached to the structural components, and then the diamond sample was placed on the stage, and then the stage can be moved in the X, Y, Z using our translational stages. And then we used a camera to be able to image it while this was happening to know when we had good alignment. So this is what it actually looked like. The image on the left shows our module, and then the image on the right shows the actual optical setup. There's a lot more equipment here, and some of that is for the confocal setup that the PhD students use. So here are some images of us aligning our fiber to our diamond. In the image on the left, image number 1, all those white dots are our microdiamonds. You can see that they're well dispersed on our glass slide. And you can see that because our camera is on an angle, there's a very narrow focal range. And then in image 2A and 2B, you can see our lens fiber, and then the bright green dot is the laser light hitting a microdiamond and scattering the light. So this scattering allowed us to easily determine when we were optimally over microdiamond, after which we could make fine adjustments by maximizing our photoluminescence counts on our detector. So this is a brief overview of the measurement schemes that we used. So for photoluminescence, we made photoluminescence counts versus the position over the diamond. We made measurements of our photoluminescence counts versus our optical power. And then we made continuous wave electron spin resonance measurements. These measurements are where you sweep microwave frequencies and then look for the characteristic resonance peaks to determine the magnetic field.
All right, thank you. So I'll go over a little bit of our results from this. So first is our photoluminescence counts as a function of position, where we start with our lens fiber position on our diamond and then move it off our diamond to ensure that the counts that we're getting are truly from our diamond. So we can see that our true counts are around 1.4 million per second, and when we're off our diamond, this drops to about 30,000. So we have an extinction ratio of about 50% in terms of noise to background. So we can say confidently that the signal we're getting on our detector is from our diamonds. We can also measure the PL as a function of input power, and this is typically done in order to determine if we're able to saturate the NV centers, which will correspond to this linear trend peaking off. Given our current setup in laser power, we weren't able to do that, but we can see that we're in this somewhat weak excitation regime. Before I show the ESR measurements, I just want to go back to this slide. So we expect to see certain dips in our photoluminescence as we sweep the microwave frequency, and this will correspond to the magnetic field. So the first measurement we did is measuring the ESR spectrum as a function of the microwave power, which is shown by 0, -5, and -10 dB. And we can see that as we increase the power, we get more contrast. And given our circuit that we were using, the 0 dB corresponds to the highest power we could use, but in principle, this could be increased for more contrast. The next thing we did is we added a magnetic field, and we can see that these peaks separated as we expect. So the peaks separating corresponding to a magnetic field of 0.1 millitesla, which is much smaller than what is required for our application. So there's a peak shift of about 2 megahertz, and this gamma is 2.8 megahertz per Gauss, which will tell us our magnetic field. So in conclusion, we designed and assembled a module for the alignment of an optical lens fiber and a microdiamond. We optimized the coupling through our free space setup to our optical fiber setup, and from our optical fiber to our diamond, and then also back to our diamond, to our APD. And this was done to get a high count rate, and we also conducted CW ESR measurements to show the diamond magnetometry. So some future works we should do is try and optimize our experimental conditions to maximize our contrast and reduce our noise. We also want to perform pulse magnetometry schemes, which should in principle give us higher sensitivity. We also want to test our device with magnetic nanoparticles, as here we were just using a permanent magnet for calibration. And we'd like to be able to integrate our device with a microwave circuit and a mechanical arm, which could allow to be more applicable in surgery. So we want to thank Professor David Corey, Maddie, Ian, and Miriam, who are students in his group, for helping us and guiding us through this project. All right, we want to thank you for your time and open the floor for questions. Thank you.
Another session is open for questions.
Yeah, nice talk. I just had a quick question on, I don't know if I missed it or if it was sort of not clear. What's the spatial resolution that you can the scanning technique? Like how close together diamond particles can be when you can distinguish between two different particles, and how small a particle can you detect?
So in principle, like we dispersed them on a glass slide as a prototype, but in principle we would have our diamond attached to our lens fiber, so it would be isolated from everything else. So we would get our spatial resolution like from the size of our diamond, but which is on the order of like a cell or two on this order. So this is kind of well beyond what you would need, as like a surgeon isn't going to be able to pick out one cell at a time. So our resolution or spatial resolution is well below what would be kind of useful for a surgeon. So yeah.
So that brings me to the second question: is when you actually mount the diamond onto the fiber,
Yeah.
do you anticipate problems with either absorption of the, I guess it's the green light you're trying to detect, through whatever you use to attach the diamond onto
Right.
the fiber? Because there's going to be another interface, there's going to be another material that possibly absorbs and
Right.
scatters.
Yeah, so yeah, we'd have to take that into account and use a material that's transparent for green and red. We also note that if we bring our fiber close to the diamond, they'll like electrostatically attract to each other. So they'll stick if we just touch them. So that wouldn't bond them and be permanent for a device, but we can at least bring them together and then use other methods to like increase the interaction.
So have you thought about how you would actually bond it? Is there really any thought to that?
So one theory that we had was using optical epoxy, which should be transparent in both the green and red regions, which you could then cure by sending light through the fiber as soon as you're well aligned with the diamond in the fiber, which should then cure it and then lock it in place and should be a very stable.
One more short question? Yes.
Very quick. So, as I understand it, the surgeon can now pick up the sensing apparatus because it's being miniaturized and scan it across. Needs resolution needs the sensitivity of at least a millitesla, which you've got. Are you done? Is that it? Where
So do you mean from that we need to do? Like, because like, I guess like,
Have you
go,
demonstrated the key events? Is there anything else? Or is this enough to address a key challenge that has previously prevented surgeons from being able to use this in the operating theater?
so in principle, our device can work. There's still some things that we would like to optimize in order to make it more practical. So we've just done preliminary testing, but we would also need to do testing like in the clinic, I guess you would say.
But are there other drop-dead issues? Poor choice of words on my part, but
No, like in principle, it should be, yeah.
that's an important point. Make it more okay, I've used up my time. Thank you.
All right.
Where do you get the fiber tips from?
So it's from, we purchased them from OZ Optics, which is a company in Ottawa. There's many companies that sell, yeah.
One of the problems with fiber tips is that they're very, very sensitive to breakage, right?
Yeah.
Lens fibers are very, very sensitive to breakage. Right? So how do you plan to?
So once the diamond is like stuck there, then we could coat the outside and then, because, yeah.
Coat the outside with what?
So some like optical epoxy or something like this.
Because the lens nature is, we only need the lens nature for initially aligning the.
So another thing is, how close does your diamond particle have to be to your iron oxide particle for it to be able to measure?
Yeah, so that corresponds to like the sensitivity. So it should be like within, let's say, like a few hundred microns or something like this.
200 microns.
Yeah.
Okay, thanks for the presentation. And then let's move on.